Okay, so this is going to be the last lecture, and in this lecture, we're going to go over sections 13.2, and I'm going to do a brief discussion of section 13.3, just for completeness. So the title of this section is, for the main objective, basically, of this section is to determine those numbers that can be represented as the sum of two non-negative square integers. In section 12.1, we talked about the Pythagorean triples, and the Pythagorean triples is basically a triple of numbers that they satisfy this equation: x squared plus y squared equals z squared. And we could think of this as, those numbers, x and y, all right, or actually the square of z, it can be represented as the sum of two squares, x and y. Now, and with this is equivalent to basically solving this Diophantine equation. And we did this in section 12.1. And we found infinitely many of them, and we gave a complete characterization for how we can generate those. All right. Now, in this section, we are interested in actually looking at what integers n can be represented as the sum of the square or of two non-negative integers. So we need to find for what n can exist non-negative integers. In other words, we're going to allow zero, basically, x and y that satisfy that equation, which we call Diophantine equation. All right. Now it's not very hard to maybe find a few solutions of this. All right. For example, 1 squared plus 0 squared is equal to 1. So in other words, n is equal to 1, and actually that can be represented as a sum of two squares. Remember, we allow 0. We take 2, let me start doing here, 1 squared plus 1 squared. This is fine. When it comes to 3, and you can see that this one cannot be written as a sum of two squares, all right? And this you can do either by trial and error, try all possibilities, or you could actually write an argument and say that there is no way to have two integers, assuming the two integers are both even and to odd and even, all possibilities, and you're going to find out this is not a sum of two squares. 4, yes, it is the sum of 2 squared, which is 2 squared plus 0, rather, squared. And when you look at 5, yes, you can write that one as a sum of 2 squares. 6, no, it is not. 7 is not. So clearly, this means that not all integers can be definitely written as the sum of two squares. Now the question is, which are, and this is the main objective, which ones can be expressed as the sum of two squares? Very simple problem. It is known since the days of Theorem, and he did contribute to the solving of this problem. So let's start with this. Now, first we're going to find out that we can actually reduce this problem to determining which primes can be represented as sum of squares. Once we know which primes can be represented as a sum of squares, then we can find that if two primes can be written as a sum of squares, then their product can be written as a sum of two squares. And the justification of this is the following lemma, which is actually a little more general than just for, if I know that two numbers can be represented as a sum of two squares, then their product can be represented as a sum of squares. These numbers need not be even the product. So here is the first lemma. And it states this: if M and N are representable as the sum of two squares, then their product and is representable as a sum of two squares. As the sum of in fact, the proof will indicate how this can be done. All right? So here's the proof. Assume that M is the sum of A squared, B squared, and N is C squared plus D squared. Then Mn is going to be AC plus BD squared plus AB minus BC quantity squared. All right, now, of course, this is like running out of a hat in here, how these numbers came to, written this way. But of course, as you know that, what is presented in books, in lectures, and so on, is, it precedes this. A lot of trial and errors and so on. So the success usually will be presented. In other words, this one can be definitely verified by squaring these and doing basic algebra, and then you're going to get that the product of the squares of these, and then you add it and so on, you get actually Mn. Also, you could actually make this one minus in here and make this one plus. So in other words, you have got an alternating signs on the two terms that are squared. All right. So this is just by going from the left-hand side, from the right-hand side to the left-hand side, which is of course this is A squared B squared times C squared plus D squared. Just by manipulation. All right, the next theorem, we're going to see which numbers cannot be represented. Okay, so we rule out some numbers cannot be represented as sum of squares, and then find other numbers or other primes, basically. And just one other thing in here, as I mentioned, this reduces the problem to looking at the primes, as you can see, because any number, once we know the prime representation, and if I know the different primes that can be represented as sum of squares, then we can obtain which basically integers are represented as sum of squares. So let's start with the first theorem. All right, this is theorem 13.1. And I want to state it a little more general, okay, than the way it is stated in the book. Actually, no positive integer, not necessarily a prime, all right, integer of this form, 4k plus 3, or n is congruent to there's no integer. We call it n, all right, of this form can be represented as a sum of two squares. Then it as the sum of two squares. For example, that's why 7 cannot be represented as a sum of two squares, because 7 actually has this form. All right. So in particular, of course, any prime P of this form, 4k plus 3 is not the sum of two squares. All right, the proof of this is very straightforward. You know that for any integer a, we have a squared is congruent to 0 or 2 mod 4. So if we have n is a sum of two squares, if n is a squared plus b squared for some a and b, then n is going to be congruent to, because if a and b, both of them are congruent to 0 mod n, then this would give us 0 mod 4, sorry. Or if one is 0, then the other is 2, then it's going to be 2. And this is it. There's no other way than this one. So this one is either 0 or 4 mod 4. This implies n, if n is of the form (4k plus 3), then it is not the sum of two squares. Of two squares. We squeeze in here the most. All right. So very, very straightforward. This is the only possibilities that actually actually I say that this is not two, I'm sorry. This one is either congruent to 0 mod 1. This is the other possibility. And with this means you can have actually 3 possibilities in here when we add them up, 0, 1, or 2. All right. Anyway, it's not going to be congruent to 0 mod. In other words, n is not going to be congruent to 0 mod 3 to be as a sum of two squares. All right. The next theorem, we're going to look at the primes of the form 4k plus 1. So this is our next target number is this. And we have the second theorem, 13.2. This is due to Fermat. Fermat sum of two squares. This is what it's referred to as Fermat's sum of two squares theorem. All right, and to state this, if P is a prime of the form 4k plus 1, or P is congruent to 1 mod 4, then P is the sum of two squares. And in fact, we're going to see that the representation of P as a sum of two squares, if it is of the form 4k plus 1, is unique. Okay, but we're going to have that one proved, separately. All right, as a corollary. All right, there are different ways that this theorem actually is proved. The author chose the proof based on a lemma by Axel Theo. He's a Norwegian mathematician. Theorem was stated in the early 1900s. And in fact, the proof is very nice. So that's what I'm going to do. Actually, just follow the author's proof. And in order to present the proof using that theorem, we're going to present a lemma, all right, that is needed in the proof. All right. So this is our target. This is our next objective, is to prove Fermat's theorem on sum of the squares of primes. But we need the following technical lemma. This one is due to Axel Theo. Theo, I don't know how this is pronounced, but slightly none of those. All right, and it reads like this. Let B be a prime, any prime. The actually, we could think of it as an odd prime, be a prime, and A, an integer, relatively prime, to P, then the linear congruence this is in x and y, in two variables, in x and y, which is ax congruent to y mod p, has a solution say x sub 0, y sub 0, that satisfy these conditions. 0 less than the absolute value of x sub 0 less than the square root of p, and the same thing for the y. All right, so this is what Theo's lemma states, and we're going to be using this theorem to, or this result to prove fairness theorem. All right, the proof of this lemma actually is constructive, means in the proof we're going to be looking at a certain set of ordered pairs, sort of, all right, and we're going to extract from this set a solution for this congruence, all right? So what I'm going to do, I'm going to illustrate the basic idea or the main idea in the proof, okay, by an example. And then, of course, we have to work on the general solution afterward, all right? But I hope the example will kind of guide you through the steps that we're going to follow in the proof. So here is the example. We're going to consider the congruence equation. Five x congruent to y mod 10. So in other words, we're going to use the prime 15, and the a is equal to 5. All right? So here a is 5, and p is equal to 50. All right. So the first thing we want to do is we're going to define this integer, call it k, and this one is going to be the greatest integer of the square root of the prime, which is 13 in this case, plus 1. And square root of 13 is 3 something, so the greatest integer for it is 3 plus 1 is equal to 4. Then we're going to consider this set S, which consists of, I don't want to make it look like an ordered pair, but it is sort of in this form. Ax minus y, such that the x is between 0 and the k minus 1, all right, which is going to be 3. All right, and the y is the same. All right, so in this set, it has actually, it's not very hard to see that the cardinality of this set, all right, it's going to be actually 16. All right. We're going to consider all possible x and y that when we plug them in here to come up with these different values, all right, these different integers. And all of these are actually will be distinct, okay? As far as numbers, they are distinct, okay? All right, now let's actually display the elements of this in a form of a table. So we're going to display S in a table. So the table is going to look like this. So in the top, I'm going to put the x values. In the bottom here, or vertically, I'm going to put the y values. And in here, the values ax minus 1. So this is going to be the result in this table. So the x 0, 1, 2, 3. And 0, 1, 2, 3. So we're going to substitute first for x and y 0 in here, we get 0. Then we're going to substitute for y by 0, x is 1, so this is going to be 5. And then we're going to have actually y again is still 0 to fill out the first row. And the y is 2, this is going to be 10. And this is going to be 15. And so on, we fill out the table. And we get -1 in here. We get 4, 9, 14. This is -2, 3, 8, 13, -3, 2, 7, and 4. So there's a total of 16 distinct entities. Okay, positive, negative, there's 0 are in there. Now, we're going to take this table or reduce this table mod 13. So we're going to consider this table mod 13. And we know that the results that we're going to get, they're going to be not all distinct this time, because mod 13 at most we have actually 13 distinct values mod 13, which is goes from 0 to 12. All right? Now, when I do this, the table becomes, in other words, there will be some values of x and y where we have the same ax minus y. They give us the same value mod 30. Now, the reason for this is because there are 16 values, and at most we have 13 distinct values. We are using what is called, the pigeonhole principle. All right. So we're going to fill out this. All right, which has 16 entries in it supposedly with 13 different. All right, only can be different up to 13. So 2 entries in here, at least 2 entries, they must be the same. All right. So what we get when we reduce the table mod 13, we get 0. We get 5 in here, 10, 2, 12, 4, 9, 1. At 2, we come up with 11, 3, 8, 0. Then we have 10, 2, 7, and 12. You will see that we have in here the 0. We have this is there, and then we have the 2 in 2 places, and then we have the 10. All right, so these are the same values for different values of x and y. And of course, in the general argument, we're going to see that, yes, there must exist 2 different values of x, all right, and 2 different values of y. When we plug them in ax minus y, they would be congruent to each other mod 12. In this particular case, I want to take the 2, for example, all right, which is this one, and this 2 comes in by having the 5 times the 3, the x is equal to 3 in here, minus 0. This is actually will be this is congruent to 2 mod 13. And so in other words, this is the ordered pair which we're going to have 3 and 0. And so this is the x and y. And then the other 2 in here as an x value of 1 and a y value of 3. X value of 1 and 3. And when we do this, 5 times 1 minus 3, this is always also congruent to 2 mod 30. You can take others is this. All right. Now we notice in here that we don't have the x values are different and the y values are different, of course. All right. And now we're gonna take the. We need to find a solution for this. I claim that if I take x sub 0, because these only fit into this set, okay, as elements in this set. So I'm going to let x sub 0 is equal to x1 minus x2, x1 being a 3, x2 is equal to 1. And we're going to take the y sub 0 is equal to, actually we could take it out 0 minus a 3, and this is equal negative 3. All right. And I claim that, which is very simple, of course, too, that 2 and negative 3 is a solution to the congruent 5x congruent to y mod 30. The congruence, which is 5x congruent to y mod 30. That's not very hard to check. This is 10. Yes, congruent to 3 mod 13. This actually does hold. All right. Moreover, of course, they satisfy the inequalities given in the lemma. That is, the absolute value of 2 is definitely bigger than 0, less than the square root of p, which is 13, and the same thing with the negative 3, and this is less than the square root of 10. So both of these actually hold. All right. Now we can proceed to present the general argument. And I hope this will, as I said, serve as a guide when we go through the steps of the proof. So remember what we're going to do first. We're going to define this K. And then K equal greatest common integer of P plus 1. So you're gonna let S consist of these Ax minus Y such that 0 is than or equal X less than or equal K minus 1. And the same thing with all. Clearly, again, the cardinality of S is equal K squared, and this is bigger than P. Okay? Because K is the greatest integer plus 1, so this one always actually does hold. All right. Now, since they are exactly P integers, that are congruent to, let's see how I'm going to say this one actually. Let me say there are exactly P congruent classes mod P, and since S, which is equal K squared bigger than P, then the mod P there are at least two values let me actually put here S in here, okay, so let me put here then S mod, we take the elements in S and do mod P, then there are at least two values of X and Y that give the same value mod P. What does this mean? There is x1 which is not equal to x2 and y1 does not equal y2 such that a x1 minus x2 not like this actually, ax1, sorry, ax1 minus y1 is congruent to ax2 minus y2 mod p. So in other words, when we plug in these values of x and y, we get the same, value mod p. That's what this one is saying. All right. Now, this is equivalent to saying, basically, that a x1 minus x2, because we're going to put the x's on one side, is congruent to y1 minus y2 mod p. All right? Now, there's one other thing in here, actually, when we are saying that actually, let me, I'm little, I'm not quite saying this is 100% accurate in here. All right, so let me actually make a correction in here. So there exists actually a different pair. Let me make this as let me make these out as an ordered pair. There is a x1, y1 not equal to x2, y2 as an ordered pair. All right, such that this is true in there. Now in here. when I have two ordered pairs, they are not equal to each other. It is possible that in one component they are equal, but not the second. Okay? And I want to, of course, in the example I have the, the two appears in two different rows, two different columns. But here they might appear actually in the same row, means that the y values are the same, but the x values are not, means they're two different columns. Or the other way around. And I want to show that actually this is the case. Okay? This is the difference between when you have an example and you want to do things in general. You have to make sure that you consider all possibilities. All right? So in here we have this x1, y1, which does not equal x2, y2. It is possible to have either x1 equal x2 or y1 equal y2, but not both. And I want to show this. Okay? So I'm going to let x sub 0, because this is what we're going to have as a solution, that x sub 0 equal x1 minus x2, and y sub 0 equal y1 minus y2. Now, to show these are not both, we're going to do it through this claim. Claim x sub 0 equal to 0 if and only if y sub 0 is equal to 0. In other words, if one of them is equal to 0, then the other is equal to 0, okay? Which makes the order pair are the same, or the other way around. So we're going to see that actually, once we prove this one, they are not going to be both the same. All right, and to do this, well, let's do the proof for this one. If I start with assuming that x sub 0, you say assume that, assume x sub 0 is equal to 0. This implies, all right, that A times x sub 0, which is x1 minus x2, all right, is congruent to y sub 0, which is y1 minus sub 2 mod b. So this implies y sub 0 is congruent to 0 mod b. Now, let's see what does this means. Now, we know that the y sub 0 is equal to y1 minus y2, and both of y1, y2 is between 0 and the square root. Actually, it is less than, which is less than or equal to k, because this is 1 less than k minus 1. And this one is actually less than or equal to square root of p. And this is less than p, right? So when we have the difference, so this means y sub 0 is the difference between these. Right, this is going to be less than t, all right? Because the worst it could happen that one of them is equal to 0, so this one is going to be less than b, and this is forces the y sub 0 is actually equal to 0. All right? On the other hand, if we assume y sub 0 is equal to 0, we assume y sub 0 is equal to 0. This implies that ax sub 0 is congruent to y sub 0, which is equal to 0, mod e. And we know that a and greatest common divisor, at is equal 1. So this implies y sub 0 is, x sub 0 is congruent to 0 mod p. And again, since x sub 0 is less than, then it makes x sub 0 must equal to 0. All right, so 1 equal to 0 implies the other equal to 0, means both of them are equal to 0 and make the two ordered pairs are equal to each other. We are assuming they are. All right, so we have actually also we have a solution because from the way we have these, they give us the same values. All right, so therefore we do have x sub 0, y sub 0 is a solution to x congruent to y mod. Right? Remember, that's what actually we said, because when we have this is x1 minus x0, it does satisfy this. This actually. Also, since we have the x sub 0 and y sub 0, neither one of these is equal to 0. And both of them, at least in absolute value, they are less than. And actually, they range between negative square root of p and square root of p. Okay? Because we could have some of them, these are negative values. And we also have this. And same thing with y sub 0 and less than square root. All right? Because these are the difference between two integers between 0 and the square root of p. When you subtract them, they will be between x sub 0, y sub 0 is they satisfy this. All right, and well, actually, any x here, the x1 and x2, they satisfy this. When we take the difference between them, they're going to be also between because they are the x's they are actually positive, but when we take the difference between them, they come to be also negative. Okay, because we're subtracting. All right. Because our next objective is to use this theorem or this lemma to prove Fermat's theorem, and that's what we will be doing next. All right. So we have. Now, to the proof of Fermat's theorem, 13 point. So we have P is a prime of this form, is congruent to 1 mod 4. Then by the corollary to theorem 9.2, I believe, which give us the Lagrange simple for -1 p is equal to 1. In other words, -1 is a quadratic residue, okay? -1 is a quadratic residue of p. This means that there exists an integer a that satisfies the x squared congruent to -1, which means that a squared is congruent to -1 mod. All right, and this in itself is of course equivalent to saying that p divides a squared plus 1. Now I'm going to be applying Theorem's lemma, so which means I need to show that this A is relatively prime to P. So I claim that greatest common divisor is equal to 1. Now, let's assume it's not. Well, the only other value this greatest common divisor is going to have is equal to P, because P is a prime. So this implies greatest common divisor is equal to P. And this in itself implies that P must divide A. We also have it from this here, that we also have P divides a squared plus 1, and then P divides a combination of this. And I'm going to take the combination as actually one other thing in here. Actually, in here, also P divides a squared. All right? P divides A, then P definitely divides a squared. All right, now we're going to take the combination of these, which is going to be a squared plus 1 minus a squared, which is equal to 1, but this is a contradiction, okay? All right, what does this mean? This means, yes, the greatest common divisor is equal to 1, and now we apply Theorem's lemma. So since greatest common divisor, A, B equals to 1, we apply lemma. And this implies there exists x sub 0, y sub 0 solution to this congruence. Where the absolute value of both x sub 0 and y sub 0 is strictly positive, and this then the square root of it. So this being a solution means that a x sub 0 is congruent to y sub 0 mod p. This holds. Then I'm going to square both sides of this congruence. Okay, so this is if this is true, then the square is true. That's what a 20 power is true. And now let's go and substitute for the A. So that implies a sub 0 square, x sub 0 square is congruent y sub 0 square mod p. But a sub 0 square, sorry, not a sub 0, just a square is congruent to -1. So we could replace this by -1 y squared mod p. And this means that 0 is congruent x sub 0 squared plus y sub 0 squared mod p. And this implies that x sub 0 squared plus y sub 0 squared is equal pk for some k. Let me use a different letter because I use the k. M coded for some. So I used the k in the previous. All right, now we know that the m in here must be bigger than or equal to 1. It cannot be equal to 0 because the left-hand side, we know that x sub 0, y sub 0 are not equal to 0. All right. Now, we also know that x sub 0 squared, all right, and y sub 0 squared. These are bigger than 0, but less than p. All right, and their sum is going to be less than 2p. Greater than 0, less than 2p. So this means that this mp is going to be between 0 and 2p. And if I divide by p, I get 0 less than m less than 2. So the only integer that is between, it cannot equal to 0. You know, m is not equal to 0, so m must be equal to 1. So this means m is equal to 1. And therefore, yes, we found x sub 0 squared, x sub 0 and y sub 0 that give you actually p. Therefore, finally, put this one in here, and this gives me. So we're able to express p as a sum of two squares. In fact, as I say, this is a constructed proof. You could find what the x sub 0, y sub 0 from applying Theo's lemma. All right. The next thing we want to show that this representation of primes of the form 4k plus 1 is unique. Okay, so this is the next lemma. Next corollary. It just states the uniqueness because we done the existence of the representation. So here it is. Corollary. Any prime of the 4k plus 1 can be represented as the sum of two squares uniquely. All right, we already proved that yes, any prime of the form 4k plus 1 can be represented as sum of two squares. So at least we know there exists one representation. So we're going to assume that P is represented in two different ways. We're going to assume that P can be written as A squared plus B squared and C squared plus B squared. Where we have A, B, C, and D are bigger than or equal to 0, non-negative integers. All right. So we're going to, of course, show that the A must equal to the C, for example, and the B is equal to the D, or maybe other types of combination. All right. So we're going to consider this quantity, which is A squared, D squared minus B squared, C squared. I'm going to be adding and subtracting the same quantity to this. So this is A squared, B squared. I'm going to be adding B squared, D squared, and subtracting B squared, D squared. And then we have minus B squared, C squared. I'm going to group these together and group these together and take the common factor. So this one, I'm going to take common factor D squared. So we're going to come up with A squared plus B squared. And I'm going to take the common factor B squared. So this becomes C squared plus D squared. Now, A squared plus B squared is equal to B squared, B plus B. And the same thing with this, C squared plus D squared. So altogether, when we reduce mod P, this becomes congruent to 0 mod. All right, what does this mean? This means that we have, there's a lot of tricks in this proof. So far, we have this one leads to this. So we have remember we have the A squared, D squared minus B squared, C squared. So we prove this one is congruent to 0 mod P. And this in itself implies that AD minus BC AD plus BC congruent to 0 mod P. Difference of 2 squares, so we do this. And each one of these implies that we have the first one. This one is either, P is going to be divisible by these and being a prime, or P divides AD plus BC. All right. Now, let's look at that. And again, we could write this one as a congruence as D is congruent to BC mod P, or AD is congruent to negative BC mod. All right, now we know that the P is equal to, say, A squared plus B squared, and at the same time equals C squared plus D squared. This implies that all these integers A, B, C, and D, they are going to be less than, or actually, or equal to the square root of P. Because each one of these is if you take this one, for example, this is bigger than or equal to A squared, and when you take the square root, you get the same thing with 4 others. All right. Then when we take for example, the AD minus BC, and all of these are less than, and this is of course is less than P, okay? When we take the difference between these, then we have this one is going to be actually less than P itself also. And together with this, okay, this makes that the difference between these implies that they must equal, which is AD must equal actually B. All right? On the other hand, when we talk about the other congruence, AD, which is plus BC, this is congruent to 0, mod B. And the sum of these, all right, each one of them is less than square root of P. So this means this is going to give me P, and P, this one is going to be less than 2P. All right, and when we do these are congruent to each other, okay, or mod B becomes AD plus BC may equal actually 2. All right. Now let's see what. So we have equality in here, and in here this could equal to P. Let's assume that this is actually is equal to P. So AD plus BC equals P. Assume this is the case, because we have an or between these. Then I claim that we're going to also find that AC is equal to BD. All right? So, then let me look at that. We have P squared, which is equal. I want to write this as A squared plus B squared and C squared plus D squared. So this is one way. And remember that when we have a product of two squares like this by the lemma that we have at the very beginning, I can rewrite this one in different ways. It's AD plus BC equal to the square, and then AC minus BD square. Do this. Now we could substitute for the AD plus BC by B, so this is equal B. And then we have AC minus BD squared. Now B squared cancel out from here, and then we end up with AC minus BD squared equal to 0, which makes the AC minus BD equal to 0. So which again means AC is equal to BD. All right, so we have now this. In either ways, we keep that equality. So the two possibilities when P divides these differences, so then therefore we have either A C equal BD, which is this equality, or the other equality which we have, which was AB equal BC. So we're going to consider all these possibilities and to determine that actually all the the two representations basically are the same. So let's consider the this. First, we're going to consider that AB equal BC. This is the second equality in here. Then we have this implies that A divides BC. You can express this. Now, but since B is equal A squared plus B squared, this implies the greatest common divisor of A, B is equal to 1. The reason for this, if this is not equal to 1, then we have the common factor between these is going to divide B, but B is a prime, so that is not the case. So this must be equal to 1. Now, by Euclid's lemma, we have A divides BC. This implies A must divide C. Because it doesn't divide B, so this must divide C. And this in itself implies that C equal A K for some integer K. And now we're going to show that this K must be equal to 1. Okay, so the claim is K equal 1. Well, let's see how we do this one. We have AB equal BC. And this implies AB equal, we're going to substitute for C by AK. And this implies AD equal ABK. Can I cancel out the A? So this means the D is going to be equal BK. And now let's again go to the, let's say there's a lot of kind of tricks in here. So let's go back to this representation of P. We have P is equal C squared plus D squared. And from here we can substitute for C by, remember C is equal AK squared plus D is equal BK squared. And this makes this K squared plus B squared, which is K squared B. And we conclude from here that K squared equals 1. And since everything is positive here, so must be K equal to 1. All right, well, with this, then we have the C is equal AK. Means, and this means it's equal to A, and D is equal BK, and which make it equal to B. So C equal A, D is equal to B, and then we have the representation of B is unique. Similarly, you can handle the second case when C is equal B. All right. The second case is similar. All right. Now let's see what we have accomplished so far. Okay, just kind of running through the different representation that we have. First, we have shown that any integer of this form, 4k plus 3 is not the sum of 2 squared, right? Then we had any prime of the form 4k plus 1 is the sum of 2 squared. And in fact, it's in any way. It's the sum of 2 squares. Now, in the first one, we say any integer. Of course, in particular, also this works for a prime. Now, if I take 2 primes of the form 4k plus 1, okay, let's look at this. Product of 2 primes of the form 4k plus 1, both of them, is a prime of the same form. Is a number of the same form. And we know that, of course, it means that this number can be represented as a sum of 2 squares by the level. So this implies such number is the product of, is the sum, the sum of 2 squared by the level. In fact, even if we don't care what type of it is, you know, whatever form it is, but it is extra to be also of the same form. How about if I take 2 primes of the form 4k plus 3? Okay, so the product of 2 primes of the form 4k plus 3. So this actually give us a number of the form 4k plus 1. All right? Not a prime, but it's going to be of this form. Here's a sticky situation because I know that the primes of the form 4k plus 3, individually they are not sums of 2 squares, but when I multiply them, I come up with a number of the different form. Question is this going to be a sum of 2 squares? And it turns out, yes, there will be. All right, and we will show this is the sum of 2 squares. But we need 2 of them. Okay, so there must be this 4k plus 3 appears at, in even form, or doubles, basically. The fifth situation is when we have the product of 2 primes, 1 of the form 4k plus 1, 4k plus 3. All right, let's see what that one will be. Of course, you can check these, okay? So 2 primes, 1 of the form 4k plus 1, and the other of the form for m plus c3. Now the product of these, it happens to be of the form product is of the form 4k plus c3. And this is not sum of two squares. Well, in other words, this means that if a prime 4k plus 3 appears an odd number of times in the prime factorization of an integer, then that's going to create a problem. All right? Because every 4k plus 3 with just one or more with 4k plus 1, they're going to produce all this 4k plus 3. All right? And because the 4k plus 1 multiplied together give you the same 4. Okay? But 4k plus 3 is going to create a problem. Well, this actually leads to the following theorem. Okay? So I hope kind of this discussion sort of illustrate where we're going to be going. All right? Is the following. And yeah, that's to give a complete characterization of the integers that are sums of two squares. All right, so this is the main theorem, and I'm going to be stating it in two different ways. One in the form, it's going to be this, and then another one to outline the, what we've been saying about the primes of the form 4k plus 3 must appear in an even number of times. All right, in the prime factorization. So let the positive integer in other words, this looks strange the way it is stated in here, but later on we're going to state it in a different one. And be written as, which we know that we can do this, n equals n squared m, where m is a square free just is a square free. All right, and we can do this by taking and take all the squares in its factorization, and put them together and call this is capital N S squared. And then those other primes, they do not appear with repeated primes. Okay, then you put them just in M. So that's where M has no square. None of the primes in M has a square, not repeat. All right. Then N can be represented as the sum of two squares if and only if M contains no prime factor of the form for k plus 6. So in other words, the prime factors of n of the form 4k plus 3 must appear with an even, all right, exponent. Sometimes, of course, maybe there's 4, 2, whatever it is, okay? But that's really what it is. It cannot appear with, single or odd, basically, exponent. All right, so this is, and let's say we're going to state it also slightly different way as a corollary or a restatement of this theory. All right, the idea is, let's assume that we have a prime factor of m, all right, and we're going to show that it cannot be of the 4k plus infinity, all right? We're going to assume that E is a prime factor of m, and if n is to be represented, now we're going to go this way first. So let's assume that E is a prime factor of. To start with, actually, maybe before we do this one, we go to the side in here. It is possible that if m is equal to 1, then we have n is equal to n squared, and sure enough, we can write this one as a sum of 2 squared in a trivial way. All right? So for this reason, we can assume m is bigger than 1. And we're going to then consider that E is a prime factor of m. All right. So then also one other thing that is if P happens to be, then we know that since we can write this one as 1 squared plus 1 squared, all right, then depending on the other parts of, the primes in P, you write it as a sum of 2 squared, then if 2 happens to be one of them, then it's going to create no problems. Now we know that I thought I stated what I want to prove incorrectly. Let me go in here, state this is correctly. Okay. So here's my assumption, I'm sorry. Let's assume that none of the prime factors of m are of the form of the form 4k plus 6. All right. Then we have this. Now the other thing is assume that m is equal to b1 up to p sub r, the prime factorization. Of m. Now we know all these primes are these are distinct, okay, and we have p I is equal to 2 or of the form 4k plus 4. Because they are not of the 4k plus 3, so it's going to be either 2 or this. So I would have one of these, to be 2, okay, and without loss of generality, if I assume, we may assume P1 is equal to 2, and the others, and then the other primes are of the form 4k plus 1. Or all of them are of the form 4k plus 1, if we don't have it. So in all possibilities, since each piece of I between 1 and R is a sum of 2 squares. If it is 2, as I say, 1 squared plus 1 squared, or the other one, theorem 13.2, Fermat's theorem tells us, yes, it's a sum of 2 squared, then by banana, the product of all the primes hence M itself is the sum of 2 squared. The sum of 2 squared. Now we're gonna, so M is the sum of 2 squared, and now how we can say that or prove that N is the sum of 2 squared. So let's say this is the case. So therefore, M is A squared plus B squared. And this implies N, which is equal, N squared M, is equal AN squared plus BN. Because you just, multiply the N squared inside, and that's what you get. So yes, it's a sum of 2 squared. All right, now we're going to go the other way around and assume that we have N is a sum of 2 squared. And we're going to show that all the prime factors of M, they are not of the form 4k plus 3. All right, so we're going to go the conversely. We're going to go this way. So we're going to assume that N is the sum of 2 squares. And we want to show that M has no prime factor of the form 4k plus 3. All right, well, let's do this. So this means implies N is equal to A squared plus B squared is N squared M, or sum N bigger than or equal to 0. Now let's take it here, let P be a prime factor of M. And let's take D to be the greatest common divisor of A and B. And this implies that A is equal to RD and B equal ST for sum are S, and the greatest common divisor of these is going to be equal to 1. All right, well, let's see what we substitute in the A and the B by this is RB squared plus SB squared is equal N squared M. And here we have this is D squared, S squared plus R squared equals N squared M. Now we know that M is a square free. D squared cannot divide. So this means that D squared cannot divide M. So it must divide N squared. In other words, this N squared over D squared becomes an integer. All right, well, let's see what we can get out of this. So this implies that S squared plus R squared, we can rewrite this equation here, okay, as N squared over D squared M. Now, since M has P as as one of its prime factors, if I take this is congruent mod P, so it becomes 0. All right, since P divides them. All right, so this implies we have R squared plus S squared congruent to 0 on P. We also have the greatest common divisors of R and S is 1. Now, we have the greatest common divisor is equal to 1. So this means that at least one of the R and the S is going to be relatively prime to P. So this implies either greatest common divisor of RP is equal to 1 or greatest common divisor of S and P is equal to 1. Because if not, then we're going to have both of these is equal to P, and P is going to be a common divisor of this. So we cannot actually have that case. All right, so again, it's either one of these, but not both. So let's assume, without the sort of generality, that assume that greatest common divisor of RT is equal to. Then we're going to consider this linear congruence equation. So that Rx congruent to 1 mod G. Since we have the greatest common divisor of R and P is equal to 1, this has unique solution. Let's call it, say, X equal R prime. So what we have R prime, is congruent to 1 mod. All right? Now, let's multiply this by r prime squared, both sides. Actually, I'm incorrect. This is not what I want to multiply by. Let's look at the actually this equation, which we have r squared plus s squared. We know this one is equal to 0 mod b. This one I want to multiply by r prime squared. So what do we get? R prime squared, r squared. This is congruent to 0 mod b. Now from here we can put these together. R prime. Let me put this in here. 0 mod b. Now I'm going to use the r prime. This is congruent to 1 mod b, so the square will give us all 1. So there becomes 1 mod b. And this means r prime s squared is congruent to -1 mod b, which make -1 is a quadratic a quadratic residue. This implies -1 is a quadratic residue of b, and it makes the -1 p is equal +1. But this implies this p, again, this is by theorem, the corollary to theorem 9.2. To theorem 9.2, p must be congruent to 1 mod 4. Implies p is congruent to 1 mod. Now, remember that p was a prime factor of m. So, what we have shown, this is the only way, this could happen, that n is sum of 2 squared is this p, this arbitrary prime factor of this form. So, therefore, no prime factors of m is of the form 4k plus 3. All right? And this completes the proof of this important theorem. All right. As I said, we're going to restate this theorem. It's different, slightly different way. And here it is. In the book, he calls it the lemma. Actually, it is just more restatement rather than it follows from this. Or even think about it, it follows from this actually. So this is a corollary. Again, a positive integer is the sum of 2 squared of 2 squared each prime factor of n of the form 4k plus 3 must occur to an even power, to an even power. So they must appear with even powers, okay? Because kind of two of them to make it a prime of the form 4k plus 1. And that's what it is. It doesn't need any proof, of course, because this is sort of what we have shown. All right. All right, the next thing we want to look at is kind of a little interesting. One may ask, how about representing integer as a difference of two squares? All right, it turns out that actually we have more integer that can be represented as difference of two squares than the sum of two squares. And we have the following theorem. Uh, 13.4. It says that a positive integer n can be represented as the difference of two squares if I know here n is not of this form. N is not of the form 4k plus 2. So all other forms as multiples of 4 with remainders will be represented as a difference of two squares. So the proof theorem form we're going to show that is this. Any number of this form is not. Okay, so for any integer, a, we know that a squared is congruent to either 0 or 1 mod 4. And if we take a negative b squared, this is going to be congruent to 0 or negative 1, or which is 3 mod 4. All right? So the negative 1 is congruent to 3 mod 4. So when I consider the possibilities of these, means a squared minus b squared, this is going to be congruent to, could have a 0, both of these. You could have a 0 from the first one and a negative 1 with the second one, which will give you 1. Or you could have a 0 from a squared is actually is 1, and the let's see how we can do this one. Okay, so if a squared is congruent to 0 and b negative b squared is 0, so we get 0. if we get with 0 and with -1, that's going to give me 1. If I take 1 with 0, 1, and then when I take 1 and L3. Okay, so these are all the possibilities. 1, 4. Right? So none of these means that in any n which is of the form 4k plus 2 is a difference of 2 squared. Right? Okay, get these. Now, the next thing we need to show that all other forms can be represented as difference of 2 squared. Because this is an if and only, means these are the only ones. So all other must be represented. And we're going to take these cases, case by case. So case 1, assume n is of the form 4k, CO is 4k, all right? Then in this case, of course, we can write n is equal to n over 4, because this is actually as an integer, plus 1 squared minus n over 4 minus 1 squared. And it's not very hard to check that actually this difference of 2 squared, if you factor it out as n, as a difference of 2 squared, all right? So this one minus the other one, okay? Multiply by the sum of these, right? Plus, I haven't done this calculation, but I think that's what you're going to get in here. So let's see, this is n minus 4 cancel out, and you have 1 plus 1. In here you get 2. And what do you get in here? N over the negative 1 cancel out, and you come up with 2n over 4, right? And I hope this gives you n. Yes, this gives you. The other cases are similar, means if you have this one of the 4k plus 1. This is the factorization you get. You can write n as n plus 1 over 2 squared minus n minus 1 over 2 squared. All right? And similarly, the other case for k plus 3. All right? Also for any prime, you can, you know that this one is going to be any odd prime, rather, in this case. Any odd prime. P is the because it cannot be of the form 4k plus 2, all right? Then any prime is the difference of 2 squared in a unique way. And the unique way that you can represent it is this: p equals p plus 1 over 2 squared plus p minus 1 over 2 squared. But you can show it is unique. This is yeah. All right. Just for completeness, all right. And I'm not going to require this is, or I'm going to not ask you this is on the exam. Is to look at the representation of integers or positive integers as the sum of 3 squares or 4 squares. All right. This is actually discussed in the book in section 13.3. All right. So let's look at the sum of 3 squares. Of course, if an integer can be written as the sum of 2 squares, then it can be written as the sum of the 3 squares, because you could just add in a 0 square. All right. Now, by allowing, to add in another square, as you can see, it is possible that there are more numbers that can be written as the sum of the 3 squares than the numbers that can be represented as the sum of 2 squares, right? Because if we want 2 squares, always we can do 3 squares or 4 squares, but other way around doesn't. For example, when you look at 7, all right, this is 2 squared plus 2 squared. No, that's too much, right? Okay, 1 squared. I haven't tried it. All right, this is 4, 5. No, that's another one, probably, right? I don't have an example one where the sum of 3 squares, all right? One of the numbers that we don't have as the sum of 3 squared was 6, I guess. 6 is 2 squared plus 1 squared plus 1 squared. Okay. So 6 can be written as a sum of the 3 squares, but not sum. But 6 is not a sum of 2 squares. All right. Then the question is, which numbers can be represented as sum of 3 squares? Well, we have this theorem, all right, which says a number of this form, 8k plus 7, cannot be represented, is not the sum of 3 squares. All right. And actually, the proof of this is not very hard. Okay. So the proof of this is very straightforward. All right. The idea is to consider all possible forms. Okay. Let's assume that n if sum of the three scores. All right? And let's consider all possibilities of one of these. Okay, means for any n. So A has these forms: 4k, 4k plus 1, 4k plus 2, or 4k plus 2. Now we're going to look at the squares. What is the square is going to look like? So this implies a squared. And I'm going to take this is one at a time and then see when we add all of these up, what kind of number we get. So for if you get A is of this form. So the A squared is going to be 16k squared, and this is congruent to 0 mod 8. Because we're going to take this mod 8, okay, because the form is 8k plus 7, all right? Then let's look at the A like this, and this would imply A squared is equal to 16k squared plus 8k plus 1, and this is again congruent to 1 mod 8. Then A, it is of the form 4k plus 2. The square is going to equal to 16 plus 16k plus 4. And if this means 8 mod 8 is 4 mod 8. And now k A is 4k plus 3. Let's make the A squared equal to 16 plus 12, 24 plus 9, which is 8 plus 1. All right, all these has a multiple of 8, so this one is congruent to 1 mod 8. Now, this is true for any integer, which is true for the A, the B, and the C. So when we are adding these up, okay, so when we add this up, the possibilities are to consider all of them of the congruent to 0. So this would be congruent to 0. Let's say 1 congruent to 0, and we have 1, and all other 0. So 1. So in other words, if you take all combination of the possibilities of having 0, 1, 4, 1, taking them as 3 of those, then you come up with these are the possible values. 0, 1, you can get the 2, if you have 1 and 1, for example, and the other are 0. And then you could get the 3 if you have 1, 1, 1. And you could have 5, 1, 5, 1, 4, and the other zeros. And you can get, you are not going to get 7, all right? And so you get this, 5, 6, but not 7. There's no way you can combine, 3 of these numbers to come up with 7. So this is mod 8. So this means n is not of the form 8k plus 7. All right. So if n has this form, then it is not, it's not a sum of 3 squares, because this is the form of the n. Must be of this. Now, we have a theorem which says that which actually numbers are also going to extend this to more. The corollary, which is this. An integer n is not the sum of 3 squares if n is of this form. Well, 4 to the m, 8k plus 7, where for any m bigger than or equal to 0. Well, we know that if m is equal to 0, yes, it's not the sum of the 3 squares. We can show it is for m bigger than or equal to 1, it's not. Okay? So it's proof by contradiction. Assume that for some m bigger than or equal to 1, n is the sum of 3 squares. And the idea is again to look at, so n we have is equal a squared plus b squared plus c squared. I want to show that we can't have one of A, B, C off, or 2 off. Okay? So this is what we're going to show this. We cannot have. So all of them actually must be even in order for this to possibly happen. All right? So if we have one odd, okay, let's assume that A is odd. And so A is equal to K 1. This implies A squared is going to be congruent to or equal, so this is equal to 4k squared plus 4k plus 1, and this is congruent to 1 mod alpha. So then the other two, they're going to be even, all right? So B, even. So this one, with 2k, make the b squared is congruent to 0, mod 4. And the same thing with the c. And this means that when we are adding them up, we're going to come up with congruent to 1, mod 4. When we add them up, this is n, but so this is going to be congruent to 1, mod 4. Well, that's going to be a contradiction because the n is supposed to have 4 to the power m bigger than equal to 1. So this can be the case, all right? So this must be actually congruent to 0 mod 4, okay? But this is congruent to 1 mod 4. Similarly, when you consider 2 of them odd, it will lead to the same thing. It will lead to a contradiction, all right? Now, this forces, therefore, we must have A, B, and C even. And let's say that we have A is equal to A prime, B equal to B prime, C equal to C prime. Now, with this n is equal A squared plus B squared plus C squared becomes equal 4 A prime squared plus B prime squared plus C prime squared. Now remember what n is, so this one is 4 to the m, then 8k plus 7 equal 4 A prime squared plus B prime squared plus C prime squared. So this is where we're able to say that if n is a sum of the 3 squares, then we can, this is forces all these to be even and these be 1. Now we can divide by 4, so this becomes m minus 1. All right, which means that we can write this one as a sum of the 3 squared. Now, if I repeat this argument over and over again, to be, this implies we're going to cancel all the 4s in here. This implies that 8k plus 7 is the sum of the 3 squared. Well, this is a contradiction. This contradicts the theorem, which says that the 8k plus 7 numbers are not sum of the 3 squares. All right? So this we get more numbers. We say it's not sum of the 3 squares by kicking in this factor of 4 to the m. It turns out that actually these are the only numbers. Means this is necessary and sufficient condition. All right? Yeah, in other words, the corollary it is an if and only if statement. It's not the it is just necessary condition. However, the proof of this is way much more advanced than we can handle. We don't have time even for it. All right? But this is an important theorem. This is a theorem by Legendre and Gauss. So I want to write it down, which give us exactly what numbers cannot be represented as sum of the 3 squared, or the other one will be represented as sum of the 3 squared. So this is a theorem by Legendre as stated in his treatise in number theory in 1798, and it also stated by Gauss. And it says that all positive integers except those of this form or to the m 8k plus 7 and bigger than or equal to 0 are representable as the sum of the three squares. We already know that any number of this form actually is not representable. But the question is, RDCCF means, any other number actually will be representable as a sum of the square. We haven't shown that, okay? I know these are not, but these are the only ones. The next thing we should look at is which numbers are the sum of four squares. And it turns out that all numbers, all positive integers, can be represented as sum of four squares. And I want to present, as I said, the proof of this is beyond, okay? It uses the quadratic forms and much more machineries that needs weeks of development to actually prove this theorem. However, I'm going to present an elegant proof of that all numbers can be represented as a sum of four squares. Okay, this theorem is referred to as Lagrange Sphere. This is Lagrange. And it was stated in 1770. So in other words, before Legendre, that he proved it in 1798. It's 1970, 1770. And it says that every positive integer is the sum of four squares. Or representable as sum of four squares. Now, again, we're going to use this idea clearly. If n is the sum of the three squares, it is the sum of four squares. Because you can add, of course, to the three squares, 0 squared, we are left at 0, then it becomes 4 squared. That's kind of cheating, but it's there. Now, we haven't talked about uniqueness and all of those and how many, different types of, how many different ways you can represent the number as sum of 2 squared or 3 squared. That's another subject in itself. All right? So in order to prove this, what I need to show, okay, since we know that the only numbers, if we accept Legendre theorem, okay, the only numbers that are not sum of the three squared, are of this form. 4 to the m 8k plus 7. Right? So all I need to show to complete the proof of this one is those numbers can be represented as sum of 4 squared. Okay? So we only need to show then these numbers. Because all others are sum of the 3 squares, so 4 squares, and we're done with those. Okay? So we only need to show 2 to show any number of the form 4 to the m 8k plus 7 is the sum of 4 squares. All right? So let's assume we have such an n, okay? And we're going to manufacture for it a sum of 4 squares. So let n equal 4 to the m 8k plus 7. So I want to consider this n minus 2 to the m squared. All right? And this is equal to 4 to the m 8k plus 7 minus 2 to the m squared. And I'm going to write this one as 4 to the m 8k plus 7. And I can write this one as 4 to the m. Okay, 2 squared to the m like this. And then I can factor out 4 to the m. And we end up with 8k plus 7 minus 1. And this is equal to 4 to the m and 8k plus 6. Now, this number, this new number here, which we obtained by subtracting from n, this 2 to the m squared, is not of the form, so this is not of the form 4 to the m 8k plus 7, because it is of the form 8k plus 6, right? The 4. So this one means this one is a sum of 3 squares. So this is sum of 3 squares. All right? Because it's not of the form, it's prevented to be a sum of 3 squares, so it is of sum of 3 squares. So this means that I can write this as a sum of the 3 squares, a squared plus b squared plus c squared. And then taking to the 2 to the other side, so this becomes a squared plus b squared plus c squared plus 2m squared. And this is a sum of 4 squared. 4 squared. And that's it. So we proved the Lagrange theorem as a corollary, basically, to Lagrange theorem. So this is an elegant to prove. However, there are very, very big problem with it, because it is based on a theorem which is way harder to prove, okay, than actually go from scratch and to prove Lagrange's theorem. In other words, as I mentioned, Lagrange proved this theorem in 1770. It doesn't need quadratic forms and all other stuff that is necessary to prove Legendre's theorem. But it's kind of a, a nice way to say that I know how to prove that every integer can be written as a sum of 4 squares. If I assume that Legendre's theorem actually does hold. All right. So what this is, I said, I just wanted for completeness in here, and to show you sometimes you could use bigger machinery to prove something that it may take a little more time to prove, but it doesn't use big theorems, all right? All right, this is it. As I said, this is going to be the last lecture. Now, if we go back, just kind of where we started about less than 6 weeks ago, and the amount of number theory or knowledge that you have gained in less than within 6 weeks or less than 6 weeks. I hope you congratulate yourself on this big accomplishment. It's not easy for anyone. I know it was not easy for you to have 2 homework assignments a week, and then every other week there is an exam. And I hope you will end up with a grade that you will be satisfied with. Okay, there's one more exam to have. And I will be reasonable, okay, and I already lowered the scale for the, for the grades. A is 85 to 100, B is 75 and above, and C, I think, goes from 60 or something like that. I see always improvement. Always I look for, improvement in your grades. If I see improvement in your, from your first exam, second exam to third exam, there's always you have improved. I will be taking that in consideration as well. All right. I have enjoyed, doing this course. It was a challenge for me because I haven't taught this course in a long time, and so I had to prepare the notes as well as the, these lectures. For you, and I hope they are beneficial. And I know it is a big challenge for you as well. So it is a challenge for everyone involved in this project. All right, I wish you good luck on the third exam, and I will be giving putting a study guide for exam number 3 actually tomorrow. Today is Monday, so it's going to be posted on Tuesday, sometimes in the afternoon. And I hope to have your also homeworks are graded and posted. I'm done with grading homework number 8. I just need to upload it and put the key for you, and then I have the other 2 homeworks. If I am unable to finish one of them, but at least I will post the solution. As far as I receive, means if you submit your homework, last homework, which is number supposed to be 10, right? Number 10. Then I will post the solution for you. All right. Take care.